Hey everybody, I hope this video finds you well. In this video, we're going to be working our way through section 2.3 from your textbook, discussing terminology for systems of linear equations. This is a relatively short section, so we should be able to knock it out in just this one single video. This section is also going to be just a little bit of a deviation from what we were doing earlier. The first two sections, 2.1 and 2.2, mostly set up matrices as a new sort of mathematical object and talked a lot about how to do different operations on those matrices, like addition, subtraction, matrix multiplication, scalar multiplication, the transpose, etc. Now we're going to switch gears a little bit and go to something that you guys have definitely encountered beforehand, especially way back when you first took like intermediate algebra. And we're going to just talk a little bit about systems of linear equations. However, as we do that, we're going to realize very quickly that systems of linear equations have a very strong relationship with matrices. And now that we know quite a bit about matrices, we'll be able to talk about systems of linear equations from a matrix-driven perspective. But to begin with, we're just going to set up some terminology for when we're working with systems of linear equations. So we're going to begin by talking about a definition for what it means to have a system of m linear equations with n variables. So let's go ahead and write what that would look like. So the first equation might look something like a11, where that's some constant, x1, which is your variable, plus a12, another constant, times x2, another variable, and that would continue on until we reach a1n xn, because we said that there would be n variables, and all that would be equal to some other constant b1. Now you'll notice, right, that in this equation, each variable, x1, x2, all the way down to xn, are in separate terms, and there are no functions being applied to x1, x2, all the way through xn, meaning there's no x1 squareds, a sine of x1, no ln of x2, no 1 over xn, nothing like that. That should remind you a lot of when we talked about linear differential equations. That's how we helped identify if something was a linear differential equation. Here, there is no differentials, there are no differential equations, but it's the same idea, even though we're talking about algebraic equations. For these things to be linear, each of the variables needs to be separated, and there can be no functions of those variables. Now, of course, what we've written so far is not a system, it's just a single equation. We said that there were going to be m equations, so we'll continue. There'd be a21x1 plus a22x2 plus all the way down to a2nxn, and that would be equal to some other constant b2. And of course, this would continue until we reach our mth equation, am1x1 plus am2x2 plus all the way down to amnxn, and that would be equal to b sub m. And as you can see here, right, in this sort of condensed notation, there would indeed be m different equations here. And if we look over here, there are indeed n variables. So that's what it means to write down a system of m linear equations with n variables there. Okay, let's talk a little bit about some names for these things. Even though it's not really necessary, we won't use it too much, but just probably a good idea to have. These aij, all these things that you're seeing here or here or here or here, those are of course just constant values, and what we call them is we call these the system coefficients, right? We call them coefficients because of course they're multiplied onto each of the variables here. Then those xi that you're seeing, those are of course our variables. And then these guys over here, those b's, those are of course also just constant values. Those b sub I, we call those the system constants, right? So again, not a huge importance to know all that terminology, but do just remember that the x's here, right, these things, these are our variables, and then everything else, these a1, a12, a1n, all these things in here, along with these guys here, those are all just constants. These, anything over here, these are considered as coefficients, and these guys are just called constants. All right, one sort of special term that is very important is that if b1 equals b2 all the way down to bm, and all of those are 0, so every equation in this format is equal to 0, then the system is called homogeneous. Now, this homogeneous or homogeneous is very different than the homogeneous differential equation that we talked about for first orders, which were ones that could be written in terms of y over x. This is the much more natural sort of definition of homogeneous, when you have a system of equations that are all equal to 0, right? And that's exactly what we mean by this here. Otherwise, right, the system is oh, it's a little sloppy. That almost looks like non-homogeneous or non-homogeneous. Okay, so just be aware that if all the equations are equal to 0, we call that homogeneous or homogeneous, and otherwise the system is called non-homogeneous. All right, let's talk a little bit more about this. We should probably define what it means to be a solution to this. So I'll give a quick definition here. A set of constants, C1 down to Cn, that when plugged in for x1 through xn, make every equation in the system true, is called a solution. So, of course, when you have a system of equations and you have n different variables, a solution is not just a value of one of the variables, it has to be a value for all of the variables. And since it is a system, when you take that possible solution, that's C1 through Cn, it has to make every equation, all m equations, true to be called a solution. Finally, we'll give one other definition here. The collection of all solutions is called the solution set. And that's the same sort of terminology there that we were using for differential equations. Some of these systems might have more than one solution, and when they do have more than one solution, the collection of all solutions is just called the solution set. Okay, let's take a look at a couple of quick examples. We're not going to really do any work here. I'm just going to sort of write down a couple examples and talk briefly about their sort of solution set and introduce a little bit more terminology here. All right, so let's take a look at a couple examples. So for our first one, right, we might have the system 2x1 plus 5x2 equals 9 and 3x1 minus 6x2 is equal to 0. Now, you guys probably know some techniques back from when you took like algebra classes for solving that. I'm not going to solve this right now, but we do want to make a couple notes with this. This would be two equations with two variables, or sometimes referenced as two unknowns. If you actually check, the solution set is only one solution. There's only one thing out there that makes this true, and it is x1 equals 2, x2 equals 1. Now, in terms of checking if that actually is a solution, that's very quick. You just pop the values in. If you pop in x1 equals 2 and x2 equals 1 into this guy, you get 4 plus 5, which is 9. Check. If you plug it into this guy, you get 6 minus 6, which is 0. Knowing that that is the only solution, well, you'd have to do some algebra to actually check that, but it is indeed the only solution here. So that's an example of a system of linear equations that has two equations, two variables, and it has a single unique solution. Whenever we do have a solution, at least one solution, we will also note that this is an example of something that is considered consistent, right? Anytime you have a solution, that means that you can call the system consistent. All right, let's look at another quick example. You can take a look at this guy, 3x1 plus 2x2 plus 5x3 is equal to 10, and then 6x1 plus 4x2 plus 10x cubed is equal to 0. This would be an example of two equations with three variables, so there's no limitation that the equations and variables have to be the same. So this time we only have two equations with three different variables. The solution set here, well, if you actually sort of just take a glance at this, even without really any advanced techniques, you can see that this second equation here is just 2 times this equation here. But if you have this equation to be true and you double it, then this would need to be 20. In other words, this has no solutions. It's impossible to solve this. So the solution set here is no solutions, or it's actually the empty set, which you can use set notation and do that. There are no solutions to this guy. This is an example of what we call an inconsistent system. There are no solutions to this. All right, one last example here. You might have this little system here. 2x1 minus x2 equals 0. 6x1 minus 3x2 equals 0. And negative 4x1 plus x2 equals 0. Now, you should make a note here, since all of these are equal to 0, this would be considered a homogeneous equation here, right? Because everything has an equals to 0. And this guy, it would be 3 equations. Let's just write that a little bit more neatly there. That's 3 equations, and with 2 variables. You can try to play around with solving this yourself, but you can also just sort of notice that while it has 3 equations, these 3 equations are actually, in fact, all the same, right? If you take this equation and you multiply it by 3, you're going to get this equation. If you take this equation here and multiply it by negative 2, well, then my bad, right? We actually want this guy here to be 2x2. Let's just make that little change there. I'm sorry. Otherwise, it wouldn't be what I actually wanted to say here. If you have that little change and you multiply this guy by negative 2, then this guy right here is going to be exactly the same equation. So while there are 3 equations, really they're all the same equation. In that case, the solution set actually turns out to be a whole family of solutions. Actually, you can solve this with where x1 is any value, t, and then x2 has to be 2 times that value. So sometimes that t that we're using here is called a parameter, and this is sort of saying that this solution set has 1 parameter in it. This would also be an example of another one that is consistent here. Now, right now, we don't actually have the mechanisms to prove it yet. We will very soon. But it actually turns out that for systems of linear equations, these 3 examples are the only 3 cases that can happen. You can have a single unique solution for your solution set. You can have no solutions for your solution set, and we call that inconsistent. Or you can have a solution set that is an infinite number of solutions. We're going to formally prove that in just a couple of videos when we're sort of working through the different possibilities for the solution sets of linear systems of linear equations. But right now, I just wanted you guys to see sort of 3 examples and see some of the terminology applied here. All right, the last thing we sort of want to do in this is just talk about some alternate ways of writing out systems of equations, basically trying to tie it into matrices. So let's go ahead and talk about that. Before we talk about those alternate ways, you should also just keep in mind briefly that there are sort of 3 main goals in what we're going to be doing here. The first of these goals, as we sort of just saw here, are what conditions are there for a system to actually have solutions. So in other words, what conditions are there for the system to be consistent? We're going to learn that there are some ways that we can sort of measure what we're studying to actually determine whether or not things will be consistent or inconsistent. If we do determine that something is consistent, the next question that we're probably going to have is how many solutions will there be? Will there be 1 solution? Will there be an infinite number of solutions? How many infinite solutions? That sounds weird, but we should know that there are different sort of sizes of infinity out there. So we want to know how many solutions will there be. And again, under what conditions will we get those different types of solution sets? And then finally, maybe the goal that sort of jumps out to us the most is how do we actually find these solutions? Now, it turns out that for our class, actually these first 2 goals are the really important ones because these are sort of theoretical goals, right? We're trying to come up with conditions to help us understand when there are or are not solutions and how many solutions we expect to find. For actually finding these solutions, we'll talk a little bit about that, but to be honest, you guys already know ways of solving systems of linear equations. It might be sort of tedious to use those old methods you learned like substitution and elimination and stuff, but you can do it. So our focus will be more on these first 2 questions, which is a little bit about that third one. All right, let's wrap this thing up by just talking about some alternate ways of writing out systems of linear equations. So this is just some alternate notation. So let's imagine we've got our system that we sort of started with, so something like a11x1 plus a12x2 plus all the way down to a1nxn equals b sub 1, a21x, oh, not bad there, x1 plus a22x2 plus a2nxn equals b2, and then we carry that all the way down to am1x1 plus am2x2 plus amnxn equals b sub m. So we've got our system there. One sort of spiffy way of writing this is sort of in a matrix notation that hides the variables because they're already sort of implicitly in this format. And that's what's sometimes called the augmented matrix notation. So this is augmented matrix notation. And this is a really handy sort of bookkeeping method that we'll use frequently when we're doing computations. So what we would do is we would write this out as A11, A12, all the way down to A1n, and then A21, A22, all the way down to A2n, and then we continue that down to AM1, AM2, all the way across to AMN. All these values here would just be those associated A values back in our system. Then what we do is we sort of put a vertical line. This vertical line doesn't really mean much. It's just for sort of visual purposes. And we put those constants, B1, B2, Bm, over here. And this augmented matrix notation basically keeps track of all the sort of important constants and coefficients in the matrix, or in the system, in a matrix form. So it's very, very sort of handy. This is very useful for computation. And we'll see some ways of manipulating this format, of sort of manipulating what we have here to actually come up with solutions to it. So very, very handy for computation. Maybe more handy in sort of theory is actually using some of the stuff that we learned about vectors and matrices and matrix operations to reformulate this. So this is sometimes called the vector formulation. So what we're going to do is we're going to let A be the m by n matrix with elements Aij. Now that sort of should make sense. We've been carrying this A11, A21, A2n notation this whole time, so that sort of is like how we write elements of matrices. So we're going to let A be the matrix that has exactly those elements. Then we're going to let X, right, this is actually vector X, be the column vector x1, x2, all the way down to xn. And then we're going to let B, which would be actually another vector, be the vector b1, b2, all the way down to bm. Then you can actually write this system of linear equations as the vector equation ax equals b. And of course, this operation right here, this A times X, that's not just normal multiplication, that is actually matrix multiplication. So what we're doing is we're taking the matrix of the coefficients here and multiplying it as a matrix with the vector of variables and saying that that must be equal to the vector of constants. And this overall is what we call a vector equation. So in other words, what we're saying is that a system of algebraic equations can be written as a single vector equation. And this format here is going to be very, very useful for when we're doing a lot of our conceptual sort of work here. All right. The last thing we want to sort of say in this is that this vector formulation that we just sort of talked about also works whenever we're working with any sort of system. It doesn't have to be just a system of linear equations, nor does it have to be just a sort of system of algebraic equations. So let's just briefly talk about how it would apply to some things that we talked about earlier back in chapter 1. So vector formulation for other things, right? So let's just imagine a little example here. Let's suppose we have a system of differential equations. Right? Maybe our system of differential equations is that y1 prime of x is sine of x times y1 minus cosine x times y2 plus x. And y2 prime of x is cosine x times y1 plus y2 minus 1. So what we sort of have here, right, is we have a system, but not of algebraic equations, of differential equations. And what we want to sort of say is, of course, we could just keep it in this form, but we could also create a vector equation for this. So let's talk about the vector formulation of this. So what we would do is we would let y of x be the vector function y1 of x, y2 of x. And we let the matrix function a of x be the matrix sine x, negative cosine x, and 1. Where am I getting those things? Well, those guys right there are those coefficient functions right there on those y1s and y2s. And then we'll define one other sort of vector function, b of x, to take care of these little pieces here, which would be x and negative 1. So now we could actually write the vector differential equation. Well, we could call this left-hand side here y prime of x. Now from our last video, you guys know that when you take a derivative of a matrix or a derivative of a vector function, you just take derivative of each component. So that would be y1 prime and y2 prime. And then we could say that that is equal to a of x times y of x. And you guys can sort of imagine you take your row times this column, and that would give us this first part. And then this row times this column would give us this second part. And then we'd put our plus b of x, which would just give us these last two components there. And so what we've done is we've taken a system of differential equations and turned it into a single vector differential equation. So this basically hints at one of the first relationship here, that any sort of system of equations can be translated into a single vector equation, because the vector is able to take into account that there are several different equations going on. All right, that's going to pretty much do it for section 2.3. A lot of this is just sort of notation and how to formulate things. In the next section, we'll actually start seeing how we can manipulate the matrices to sort of solve systems of linear equations and actually also help us understand their solution set.